So now we're going to take a look at some problems that involve conservation of energy where energy isn't exactly, quote, conserved. Now, of course, energy is really conserved, but what has happened is that some energy has either been added to or subtracted from the system. And we call energy that is added to or subtracted from the system work. In fact, work is defined as the change in a system's total energy. Now, if the force is along the direction of motion or against the direction of motion, then we can say that work is equal to force times distance. And we will confine ourselves in this class to problems where the force is either parallel or anti-parallel to the direction of motion. So the work would be force times distance. Now, if the force is in the direction of motion, then we would call it a positive force. If it's against the direction of motion, we would call it a negative force. So let's see how all of this applies to this conservation of energy problem, asking what is the final velocity of the car. So we have a car that starts off with a speed of 3 meters per second, has a mass of 1,000 kilograms, and apparently there's a force acting over a distance of 30 meters on this car. And this force is only 25 newtons, so it's not all that strong, and it's acting against the direction of motion of the car. So here's how we would write our problem out. We would start off with conservation of energy. It's probably good to write the givens first, but we'll at least set it up and then we'll write the givens. So your conservation of energy statement is total energy initial plus work equals total energy final. So that becomes kinetic initial plus gravitational potential initial plus work. Well, that work is force times distance equals kinetic final plus gravitational potential energy final. And since there obviously aren't any springs, I didn't bother adding any extra subscripts to my potential energy, because it would, in truth, it's zero anyway, because there isn't even any gravitational potential energy change here. It stays at the same height. So we make note of that and realize that this equation up here just becomes kinetic initial plus force times distance equals kinetic energy final. So now we'll write down our givens and write out the fact that kinetic energy initial is 1/2 mv initial squared, that work is force times distance, which we already did before, and the kinetic final is 1/2 mv final squared, having already canceled our u initial and u final terms. And I'm going to do this the good algebra way, and we're trying to solve for the final velocity, so that means we're looking for v sub f. So it's embedded in this term, so we're going to multiply both sides by 2 to get rid of the half. We're going to divide both sides by m to get rid of the m, and then we're going to take the square root of both sides. Now, in these types of problems where we're dealing with work, it might actually sometimes be a good idea to plug in the numbers first and then solve for your variable at the end, because that'll give you kind of a conceptual understanding of how much energy exists where. But we're going to do this one completely algebraically first and then plug in the numbers. The second problem that we'll do in this little video is one where we plug in the numbers earlier on. So here we go. I have multiplied both sides by 2. That got rid of this half and put a factor of 2 right there. And I've divided both sides by m, so that got rid of this m, and it put a denominator of m over here, so that's why we have a 2fd over m. Again, the 2 comes from the fact that we multiply both sides by 2. When you multiply or divide both sides by anything, then the distributive rule applies if you have terms added or subtracted on one of those sides. So then I take the square root to solve for v sub f, and I plug in my numbers. And when I do plug in my numbers, I get a final answer of 2.7 meters per second. So now let's take a look at another type of problem. So let's say we have a force of 4,500 newtons acting over a distance of 10 meters, and then this car also climbs a hill, and we're wondering what speed the car has at the top of the hill. So in this case, we use the fact, okay, it acts for 10 meters, so there's our distance. So we write out our givens. We have an initial height of 0. I again emphasize that it is wise to make either your initial or final height 0, if you can. And that force is 4,500 newtons. Now this time the force is acting in the direction of motion. So it's a positive force this time. And we have our mass, we have our initial velocity. So we start off with, ta-da, conservation of energy. Sum of initial energy plus work equals sum of final energy. In other words, what you had to begin with, total initial energy, plus what you added, work, equals what you have in the end, total final energy. So we write that out like this. And now we write out what each of these terms actually means. Now, I plugged in 0 for my initial gravitational potential energy because at the beginning, my height is what I'm calling 0. So I set that entire term to be 0 because that's an MGH. One of those terms is 0. They multiply together, so the whole thing's 0. And we're trying to solve for our final velocity here. So I subtract MGH from both sides, where that's MGH final from both sides. And then I multiply both sides by 2. So there's where this factor of 2 comes in, that factor of 2 comes in, and the half goes away over here. And also notice that going from this line to this line, I have switched sides of where I'm putting my 1/2 mv squared. In other words, I used the reflexive property of equations. Now I divide both sides by m. Now, if you canceled mass in this problem, instead of dividing both sides by mass, which leaves one term with mass in it, then you should mentally give yourself 0 credit for this problem, because canceling only works on a problem like this if there is a mass term in every single term. And there's not, so you can't cancel them. You can divide both sides by mass, that's legal, but you can't. That division will not result in it completely canceling. You have this over m right here upon doing that. It gets rid of the m here and here though, so it makes things a little bit easier, maybe. So I'll now take the square root of both sides, plug in my numbers, and when I do that, I get a final speed of 6.34 meters per second at the top of the hill. So apparently, if this car is going faster at the top of the hill than at the bottom of the hill, that force that was acting on that car must have given it a whole lot of extra energy. And indeed, that's exactly what happened. So now let's turn our attention to a problem where work applies twice. So here we have an F-14 fighter jet flying levelly, which means no change in gravitational potential energy for 6,200 meters. But at the beginning of this distance, the jet was flying at 195 meters per second, and the engines exerted this much force over the first 2,500 meters. And then air resistance is adding a constant 22,500 Newton force over the entire distance of 6,200 meters. So the question is, what is the final speed of the jet? So we think about what is actually going on here. We have the engine's force doing positive work, and the air resistance force is going to end up giving us negative work here. So write down our givens. We have the mass of the jet, initial and final height, which turn out not to matter. In fact, actually, the initial and final height are anything we want. This could say anything. I could put 0 right here. In fact, there's really nothing to indicate that it actually is at 6,200 meters. I just picked that number because that's also the distance the jet flies, but I could have picked any number. Now, the initial velocity, 195 meters per second, that's listed. The force of air resistance is listed. The distance over which the air resistance acts is listed. The force on the engines is listed, and the distance over which the force from the engines acts is listed. Now, I screwed something up here, just realized that, but if I go back and edit it, then it would change up all the animations, and that takes too long. This force right here should be negative. It's a negative force of air resistance. The force of air resistance is opposite to the direction of motion. So that's going to show up eventually as a negative anyway, though. So we have our givens here, except again, this should have a negative 22,500 newtons. So we have the total initial energy plus work by the engines plus work by air resistance equals total final energy. So what is total initial energy? Well, you have kinetic energy, and you also have potential energy due to gravity initially and finally. But of course, those cancel because the jet is flying levelly. There is no change in h, which means no change in gravitational potential energy between the beginning and the end of the problem. So now we continue and plug in what each of these are. Now again, technically this should be a plus FD, where I make F itself negative. So we'll just say that we're going to deal with magnitudes of these and plug them in like so, but yeah, if we're being more careful, then we would have plus force air resistance, distance air resistance, and force air resistance itself would be negative. Either way, the math works out the same. So now we're actually going to plug in the numbers first. We're doing that in this case so that we can get an idea of how much energy each of these terms contributes. So we plug in our numbers like so, and then calculate them out individually. So apparently the kinetic energy of the jet initially was about 570 million joules. And the jet's engines added about 140 million joules during the flight. But unfortunately, the force of air resistance ended up subtracting about that same amount during the flight. So we have that, and we solve for the final velocity. Notice I've already taken my 1/2 of 30,000 kilograms, and I get 15,000 kilograms. Now, it should be no surprise that your final velocity in this case ends up being 195 meters per second. And that was because of the fact that the force of air resistance turned out to exactly cancel the force from the engines. That won't always happen. In general, the answer at the end is going to be different. Now, on your screen, the 195 doesn't show up, so let me bring that down. There we go. So now the 195 meters per second is showing up, but I got rid of some stuff at the top of the screen so that you can see the whole thing. So that is how you can use work in conservation of energy problems to solve for unknown quantities. So if you have any questions on this, please let me know. Thank you.